hackers comes to Troopers, we contact them directly. Like we identify, say, a certain topic as relevant, or we see somebody. I mean, including myself, we are active speakers ourselves, so we are at a lot of conferences, and it's like, okay, I've seen something, a good talk over there. Let's contact the guy. And mainly, to be honest, for a bit of visibility reasons, at some point in the process we put out a CFP. But at the time, it's usually two or three slots left. And we just put this usually on full disclosure. We do not even take much care of that. The funny thing is, this year for those, say, 2 or 3 slots, we got about 30 submissions. Which means you have to put some scrutiny in there, like, oh, let's discuss, is this interesting, what do you think? But there was one submission which came in, and even without consulting the other guys, I decided, okay, this is this guy is in for a talk, and this was David Weinstein. I went through his abstract, and I immediately knew this is going to be cool stuff. So you had an answer within an hour?
Yes,
or so after
it was very fast.
And again, I took the liberty I have as say, given my hierarchical role in certain circles, not going through the official PC or board discussion, but deciding on my own. This is something I want to see.
Well, thank you.
David, high expectations, but
yeah, no pressure. Well, thank you for taking that risk with me. I hope you all enjoy this presentation. Okay, so I'm David Weinstein. I work at Via Forensics, the company based out of Chicago, focused on mobile security. And part of my job is to do research in mobile security. And so basically what I'm going to present today is some proof of concept for Android platform. And I want to do it in the context of this idea of corporate espionage, because it's a big deal and it's happening in large scale, I believe. So corporate espionage, what is this? Perhaps the state of corporate espionage is a result of increased reliance on computerization. I mean, certainly James Bond makes this really sexy stuff, right? So it's kind of fun to talk about. But what I'm really focused on is the mobile, what is the risk of these mobile platforms in a corporate setting? And what we've seen, at least in most cases, from small beginnings come great things, right? So in the case of RSA, it was simply an email that started the whole chain of events that led to RSA secure ID tokens being stolen, right? So it wasn't something very complicated or sophisticated. An email was crafted. And it ended up being an email that landed into a junk email box, right? The user actually went into the junk email and found and clicked on that URL, clicked on that document, I guess. So clearly, the level of sophistication required to get into a corporate network isn't set all that high these days. This talk is a little bit more forward-looking, trying to look at what are the possibilities with mobile platforms. So, the comment that I'd like to ask is, it's just business, right? This idea of stealing information. Perhaps there are nation states that are doing this. Perhaps it's company to company. But for the most part, it's for business or national gain. But yet, the FBI put out a report saying that $13 billion have accumulated in loss of intellectual property. So I don't know how they put a number to this. But obviously, it's of interest to the US government, and I'm sure other governments, where this intellectual property is going and how it's leaving. And the question is, what is of interest? Clearly, information and communication systems, military stuff, healthcare, electronic information on patent pending, results, research and development. All these things are of particular interest in a corporate environment. And basically, we find that more and more cyber, and I probably should drink when I say that, but it's easier to do it via computers because the lack of attribution, and you've heard all these other talks talking about how hard it is to attribute things to a particular country. And the level is set very low. I mean, clearly sending an email with an attachment is not that hard. So there's this big question of how is this problem going to be solved, but I guess the angle that I'm going to take with this talk is to just give another example of how things can be done and try to talk about some potential mitigations for those attacks. And I'll show a couple of demos, which I'll talk about in a moment. So the question is it, what's happening? We've just really been tracking things from 2009, at least in the news, talking about Aurora. Unfortunately, this image doesn't show up very well on this projector, but basically, I'm trying to put across that, there's a lot of public attention to this stuff. And the more attention there is to it, the more likely it is to happen, in my opinion. So the question, is it real? So I have a video here. I don't know if it'll play with full audio, but I will try. Let me just go back there.
Beautiful, unethical, dangerous. You've turned every cell phone in Gotham into a microphone.
And a high-frequency generator receiver.
You took my sonar concept and applied it to every phone in the city. With half the city feeding you sonar, you can image all of Gotham. This is wrong.
I've got to find this man, Lucius.
At what cost?
The database is null key encrypted. It can only be accessed by one person.
This is too much power for one person.
That's why I gave it to you. Only you can use it.
Spying on 30 million people isn't part of my job description.
This is an audio sample. If he talks within range of any phone in the city, you can triangulate his position.
I'll help you this one time. But consider this my resignation. As long as this machine is at Wayne Enterprises, I won't be.
When you're finished, type in your name.
So this video sort of captures a lot of interesting topics. You have the question of, is it right to do these sorts of things? Is this audio coming through okay? Yeah. Okay. So there's a lot of questions here in this video and a lot of interesting potential answers, I guess. And I like it because it summarizes them all in one short 1-minute clip. But the question is, how real is that? Is it possible to do this sort of thing with mobile devices? And here's a interesting piece of research from this researcher, Art Templeman, who's at the University of Indiana. And he basically created an application that opportunistically takes pictures from mobile devices and combines that with accelerometer data from the sensor on the platform to create these very interesting 3D models of rooms. And from that, they were able to extract information like barcodes, checking numbers on Swift codes on checks, and so many different interesting artifacts from a setting. So they called this information burglary from a mobile device. So that's a kind of a cool, interesting idea. And they didn't have to work that hard. Certainly, building these models was challenging, but we're at a point with with our capabilities with visualization and 3D modeling that we're able to do these things quite rapidly. So it's quite interesting. So next, I'd like to talk about these things in the context of a kill chain. So the kill chain is basically 8 steps in a process of a typical hack, right? In the case of mobile, it's a little bit more complicated. You have more potential attack surface. But this is a useful way to talk about how an attack happens, where you can sort of defend things. And it's basically how I'm going to walk through one of the demos that I'm going to do. So on the left, we have before hack. You do reconnaissance. You might weaponize some kind of exploit. you deliver, and then use the exploit against the target. So in the gather intelligence phase, in the case of mobile, one of the most useful things you can gather is the serial number of the device, when and how the user charges this device, which will be useful later. You can get all sorts of device fingerprint information. The interesting thing is that the majority of things you can get from reconnaissance you can do with basically an advertisement library sitting in the application. A lot of that information is basically gathered by these advertising libraries, and people don't seem to care that much. Of course, as an adversary, you have to prepare some kind of exploit or an attack for that particular device. In my case, I build a custom kernel for the Android device, the target, so I'm going to end up installing some kind of rootkit on the platform because I'd like to have low-level access to things inside the kernel. Of course, when it comes time to delivering a payload to the application, we have many options. In the case of Android devices, it's very easy to basically dynamically download an object from a website and load that into memory. Whereas on iOS platforms, that's far more difficult. It's generally not, it's not nearly as easy. So in the case of, let me just go back for a second. So in the case of the demo that I'm going to do in a moment, basically we've created a demo RSS application. So the idea is that the user has downloaded an RSS application for browsing, going, downloading Slashdot articles or Reddit articles, and we use the fact that we can dynamically extend the functionality of the application to load malicious content. And then, of course, you have to execute the exploit against the target, load the malicious code. In this case, I'll be installing some kind of user space application level RAT and a kernel level component, mostly because it's a lot easier to do things at the application layer to gather data, because there's this semantic gap. When you're looking at things from the kernel space, things look a lot more abstract. And if you're able to extract information from user space, it's much easier because you can just call the appropriate APIs. So you basically have the ability to get information at the kernel level and information at the application layer very nicely. Command and control. So once the target application is run on the device, it'll connect back to our server. And this is all pretty typical for normal laptop and desktop platforms. Of course, you have the challenge of the mobile network going down, so you have to be resilient to network comm being different, that sort of thing. And then, of course, if you have some objective, right? So in the first demo, my objective is just to gain access to the platform and extract all sensor data and any contacts lists and as much data that I can get from the platform itself. In the second demo, I'll basically be using the phone to actually start a whole nother kill chain. So you can have kill chains within kill chains, sort of recursively defined. So in one case, I'm going to use one kill chain to get access to the device, and the other kill chain, I'm going to use the device's, leverage the device to basically get onto another device. And of course, you have to be stealthy. So we heard talks about interesting techniques for doing covert channels, but for the most part, you don't have to employ these sophisticated covert channels because these mobile networks aren't looking at these sorts of communication channels that closely. Do you believe that your infrastructure is actually looking at this sort of thing? Not really, especially if it's just very simply encrypted. And of course, there's no shortage of sensors on these platforms. In the case of the demo, I'll be using all of these sensors that are in green. So I'll be able to take pictures from the front camera, the rear camera, exfiltrate data through the baseband, Wi-Fi, gather information about local wireless networks, Bluetooth devices. All this stuff is not really new, right? We kind of expect all this kind of sensitive information to be gathered from the device. So the first proof of concept is just saying, hey, this is possible, but also in the case of the front and rear camera, that there's no feedback to the user when these things are happening. Turning on the microphone, for example, that's It's actually not even on there. But turning on the microphone, there's no feedback required to the user. It's not like I need root on the platform to turn on the microphone, and I don't need root to make it look like there's nothing happening to the user. It's just part of the APIs to let me do that. And that's kind of scary. Okay, so this first demo, you just switch. So the first demo, I'm going to use this Galaxy Note 2 device. You guys have probably seen these all over the place, right? So you'll see here on the screen, hopefully down here, you'll see that there's an RSS application running on the platform. If you guys want to move up a little bit to see, if, that's fine. But basically, the idea here is that the user has downloaded what seems like a non-malicious application, very useful application. And what I'll show is that we can very easily, dynamically increase the capability of this application. And so if I get my terminal up. So if you look at the monitor here, you're going to find that through cloud messaging, I'm able to dynamically add a new RSS feed to the application. So you see this new entry at the bottom here, Via Forensics. Everything works just great. You can browse the latest news about Via Forensics. Nothing's really going on right here at the moment, just basically right here. But then we have another command that we can send to this application. Just switch over. So here we see that now on the Exynos on this Galaxy Note 2, basically I popped up a wrap. This application sits on the device, and I'm doing it in a way that's not stealthy at all, and basically want you to see that something's happening. This application is basically connected back to my server already. So in theory, I should be able to come over here. And there we go. And you can see that this device has popped up on the screen. And on the server, we can get all sorts of interesting information, like the IMEI. This particular device doesn't have a SIM card installed, so I don't have as much information, but we can see things like local wireless access points, get their frequency and dBs. We can get any Bluetooth devices that this particular mobile device is paired with, potentially trying to talk to those devices if we like. We can do all sorts of funny things to the device itself, like send a vibrate command. So if we really want to creep the user out, you guys, I don't know if you can hear that, but the phone is basically vibrating. We can send messages to the user. So if you see on the screen there, there's basically a hello being sent to the user. We can send a URL. So here we are going to Google, right? So if you don't have a payload on the device that you'd like to have on the device, you can just go back to your HTTP. We can take pictures. So would you like to take a picture from the back camera? No, let's use the front camera first. So there's the perspective of of course, the back camera isn't nearly as interesting unless I hold it up. There you go. That's a pretty cool one. contacts list. Oops. Oh, that's a bug. This particular device has so many contacts that I think I've actually crashed the server, the client there. We can also do things like send SMS, get call logs, all sorts of great stuff. I'm also going to just get this other phone running, because for the second part of the demo. Let me go back to the slides for a minute. So, you know, the comment here is that mobile is different. Not only is there a ton of data on the phone that we can use, right? But the phone goes to places that a normal computer laptop doesn't go to, right? Here we have an interesting picture where people have purchased a case so that their phone can go underwater, right? Would you ever do that for a laptop? No. Doesn't seem very likely. But these phones go into business meetings, right? We walk in, and actually I didn't even show that I can turn on the microphone. I'll do it on the next one. You know, you can definitely do audio hotspotting. You can do processing on the phone to figure out when you'd like to turn on the microphone. Just keep it on and only send back things that are of interest. So mobile is definitely a bit different than our typical technology and has an interesting attack surface, but also additional interesting things to pull off the device. So I've shown that you can steal location, right? You didn't see audio and video yet, but Android offers sort of rich set of APIs that you can do these things with ease, right? So as we increase our feature set within the application space, we make it that much easier for an attacker to use those. And there's no shortage of vulnerabilities. I compiled a list of over 100 Android root exploits. I can provide access to this list, basically just keeping track of who has done research on what. But there's so many Android exploits out there that there's tons to choose from. In this particular case, I use an Exynos vulnerability for Samsung. So the Galaxy Note 2 has this file on the file system that lets you read and write to all of physical memory. So Samsung gave it read-write privileges to everybody on that platform. So any application with no privileges at all can read and write to RAM. It just seems kind of wrong. There's a lot of these devices out there. Luckily they patched it, and hopefully you have a patch on your device. But you know, there's all sorts of these interesting sorts of vulnerabilities. We also see lots of vulnerabilities that use race conditions, basically racing to create a symlink to a file system device. So we usually have one application that's trying to get a system service to create a symlink to a file and have it overwrite that file with data of interest. And unfortunately, on Linux, there's not much you can do about that except try to keep these race condition windows very limited. And a lot of these bugs on here are just race conditions for file creation. Of course, Android devices can behave and interact with a lot of other devices. So they're designed to interact with other machines, right? You plug it into your computer to use Ethernet to basically do tethering, right? We have audio docking, which is kind of an interesting thing. I mean, obviously iOS has had it forever, but Android's been kind of slow to get this to work. But you can plug your phone into another docking device and pump audio out of the phone. So how are these things implemented? Well, they're implemented in the kernel, and they're done with this thing called the Linux USB gadget framework, which I'll talk about. And basically, with root privileges on the phone, we can, which I got through this Exynos vulnerability, we can add functionality to the kernel and make it turn into arbitrary devices. So if you were downstairs at Travis and Sergey's presentation, you heard about them using the face dancer to emulate all of these other devices. Well, I can do that from a mobile device. I can do all those things from a mobile device, and I can basically take advantage of the fact that I have all these sensors to potentially create a more sophisticated attack against your target system. So I would definitely use a face dancer to find and exploit these vulnerabilities, and then I would probably use a mobile device to implement and use that as a payload transfer device, because I can morph it to whatever I want. And it's very likely right now for people to plug in their phones to their computers for charging purposes and data transfer purposes. So this next demo is basically showing how we can turn the phone into a hit device. And I love this picture because it gives it, it's perfect for that. So I'm going to send one more of these. Just going to send it to my other device here. Whoops, I've got to change the cameras. So basically what I'm doing is I'm reprogramming the exploit to connect back to different repeaters because this particular system on this network has changed.
Trading dot after the 35.
Thank you. Now we have another mobile device on here. This one does have a SIM card. And we can see, all the SSIDs on the devices. But now we can enable this extra mode called plug monitor, which basically just waits for a USB connection. So I just disconnected it, reconnect. And in this case, I'm going to plug it into this Windows virtual machine that I have over here. And I'm going to show that we can send keyboard commands. And already we can see, at least in this device listing, that we have human interface devices, more than we should have. So I have a little key recorder. And basically I can type in here. So, all the keystrokes that I send are basically being piped into this virtual machine via the phone's USB connectivity. So you've probably seen something like this before with like a teensy device, but why not use a mobile platform, right? We can also send file content. So I'm just gonna, there's no way anybody can type that fast, right? So, if you're familiar with Calpelia, I don't know how to actually pronounce it correctly, but this research by Nikhil Mitt is very useful for this sort of thing. So you can use PowerShell commands. So kind of in summary of this particular demo, BYOD, well, I don't think of bring your own device, I think of bring your own demise. Right? It's not a really good idea because, well, if it's this easy to compromise mobile devices, and it's this easy to, create a morph the device on command, well, we're going to have some problems with BYOD. There's all sorts of problems, but this is just another example. So this versus the teensy device, well, there's a potential for smarter attacks. I obviously haven't taken advantage of combining the sensor data that I have from the platform and saying, hey, the device has stopped moving. I can take a picture and say, hey, there's kind of like nothing above me. I can say, I'm going to turn on the microphone and I'm going to wait till it's quiet. You can basically do light sensors. You can see if something near the phone is sort of masking the view of the device. So you can combine all this information and say, hey, I'm going to make a really smart hit device, and combine that with arbitrary mass storage. So by default, the Android devices support mass storage, right? So if I put my payload onto the mass storage and then type a keyboard command into the device and have it execute that payload from the mass storage, well then I've won that way as well. So, but it's interesting that all of these PowerShell scripts that Nikhil has worked on with T, they're definitely relevant in this scenario as well. So let's just break this down. Android uses gadgets, ADB, NTP, docking, network, and tethering. So let's add a keyboard. So my hope here is to try to teach you guys a little bit about how to actually do this keyboard stuff. And that it's not that hard. So here's a patch for the Android kernel. Under 200 lines of code to add this functionality. You only have to make changes to 2 files. And actually, I have a lot of comments in my code, so it's smaller than 189, which adds up to 8 over here. A little background about how USB works. So USB has this concept of endpoints, and we basically have one endpoint by default. We get endpoint 0 out, which is basically how the master device, the host device, talks to the slave. So we have these other interfaces, one of which we'll create is the HID one. But by default, most Android devices have ADB, which is used for debugging. So basically what we're trying to do is set up these little pipes, just like we do networking, right? And there's an API for that. It's not nothing complicated. Here's an example of a HID descriptor. So you might have seen something similar in Sergey's presentation. This is exactly taken from the spec. Just copy and paste it into my kernel source code. Or you can steal a descriptor from a variety of devices. So here's an example of Apple's internal keyboard. So we can potentially emulate Apple, the internal keyboard that's built into the laptop, to the interface. So we can just grab these bytes and come to the website as we did that last slide. Or you can get these things from LSUSB. And as always, I always like to say, use the source. If you were to go to look at the Android kernel source tree for the Android kernel, and go to drivers USB gadget, you would see something like this list of files. The interesting stuff is implemented within these files. The Android.c file defines a static list of functionality. So we have here ADB, ACM. ACM is serial port. MTP is a media transfer protocol, which is how you transfer pictures and files from the phone to the host. PTP is the picture transfer protocol. So everything you kind of expect is right here in this file. And basically, we're going to add another one to this list, the HID function. Other interesting, other ones to note is the composite and this endpoint autoconfig file. Composite basically is what allows us to have multiple protocols within one USB connection. So we can compose multiple protocols together, and basically when we plug in the device, the operating system looks at these, looks at this descriptor, which is basically going to be created for us by this composite file, and Windows or Linux will basically load a separate driver for every interface that exists in that descriptor. So if you wanted to do fuzzing on mass scale with USB, well, you could create 10 or 16 devices all talking to the device at the same time. So you could find interesting bugs about what happens when I have 3 USB devices talking and sending random garbage to the host machine. So composite kind of takes care of that for us. Endpoint autoconfig basically automatically sets up the communication. So in this previous slide, I showed how these endpoints kind of work. You create one endpoint for input stuff and one endpoint for output. And the way that USB works is that the master pulls the slave for information. So we don't even have to worry about setting up how these endpoints are set up. We just have to tell the Linux kernel that we have a device that requires 2 or 3 endpoints. They have to be configured in and out. And it takes care of all that stuff for us. It's abstracted away. And then the actual individual functions are implemented in the set_accessory file, _ACM, and ADB. So we know exactly where to look for those implementations. One of the challenges, Well, this stuff is in the kernel, right? So if you're in user space on an Android device, you don't really get access to the kernel, so you have to have a root. They're declared statically. That list, that C structure is statically declared, so it's difficult to make changes to it unless you can at runtime do so. Thanks. So we have basically two options, recompile the kernel or patch it at runtime. So depending on how skilled you are at patching Linux kernel at runtime, well, you can just recompile the kernel. And it's pretty easy to get the Linux kernel source because all this stuff is open source on Android. You just request the kernel from Samsung or Toshiba or Google. It's pretty simple to get this. In order to integrate with the rest of the Android platform, you have a couple of callbacks. Callback functions that you have to implement. So you have init, cleanup, enable, handle, bind config, unbind config, and a control request. So I'm basically just going to talk about this init and this bind config function. And I feel like everything else is pretty simple from there. So this hid function init, what all does it do? I'm sure not all of you have done Linux kernel hacking in the past, but I feel like this stuff is pretty easy to follow. KZalloc is the equivalent of malloc in user space. So you can allocate a structure the size of the hid function config, which is basically the hid function config is that list of callback functions that I showed you earlier. So that thing on the bottom right, that's basically what we're taking the size of. And then we'll just set up a couple of options in that config file, in that config structure, and call this other function, ghidsetup, which is in this wonderfully available C file called f_hid. So it turns out that the Linux kernel already supports hid devices. So we just have to connect these functions together to make this attack work. We don't have to actually implement the hid component. In that ghidsetup function, we basically allocate a character device so that from user space, we'll have this new file in the /dev tree called hidg something. And this is how in the kernel you create that, really easy. Allocate a character device with a certain value and call it something. To bind basically the functionality of the hid device to the Android system, we basically have a wrapper function for this other function in fhid called hidgbindconfig. So hidgbindconfig is already implemented for us. We just have to connect the pieces once again. And how does that work? Well, this one's slightly more complicated. We still have to allocate some extra data structures. But basically, this part is the meat of what makes a hid gadget, because the way that the USB spec works, you define a couple of fields in your USB descriptor, and basically you just have to set these values to particular things that you can get from the USB spec. Luckily, the Linux kernel people have already put that stuff for us, so we don't have to do that. But if you were interested, you could go look up in the USB spec what these values actually are, and they come from our F descriptor, which was a little bit earlier. And then we basically call this USB add function, which is a composite function. So this is implemented, USB add functions implement the composite C file. Once you do this, and if you're recompiling the kernel, you have to write it to the Android device, reboot. But once you've done this, you'll have a new file in your dev tree called dev-hidg0. And in the case of the phone that I was using, I actually have a keyboard and a mouse. So I would have a dev-hidg0 and a dev-hidg1. I could have 1,000 or 100 keyboard devices if I wanted to. And they would basically just show up as dev-hidg101, just whatever. And if I want to write data to that device, I basically just take 8-byte sequence, mostly of zeros. And this particular example sends the A keystroke down. So the way that the USB protocol for HID devices works is you have 8 bytes per key press. And within that 8 bytes, you encode what keystroke is being held down. The first byte on the left is what modifiers you're holding down, so like Shift, Control, Alt. Those are encoded in the first byte. And then a couple of bytes into this, so the next byte, the 0, 0 here, the second byte is always 0. It's reserved. And then after that, these 6 bytes on the right, they encode what keystroke is being held down. So in the case of A, it's just the 4 key. And then if we want so that'll basically hold down the A button from the host perspective. So it'll basically just repeat A over and over again. In order to get that button back up, we just have to clear that bit. And then the phone will stop sending that keystroke. If you wanted to send the B key, increment 4 by 1 and do the same thing. And you can send multiple keys down. So actually, you can increase your rate of typing if you get the timing right. Send 8 bytes, 6 bytes at a time. So, in summary, how hard is it to do Android hid stuff? Not that hard, particularly because the hid stuff is already in the kernel. We're not limited to doing hid stuff. We can do all sorts of other things. We can emulate other devices. And Android and the Linux kernel give us by default the mass storage and MTP and all these other devices that we can just use as is. So it's not super challenging. The question is, how can we do this at runtime? And that's a little bit more challenging because of the way the Android structures were built up. They weren't set up to basically be dynamically registered. So you'd have to go back and replace some of those functions within that Android data structure. And that takes a little bit more work. But basically, you wait for the plug event, and you own the machine. I love this red button. I don't know if you have I have one of these on my desk. So, I mean, in summary, basically, I wanted to show how it's possible to do these kinds of attacks. I wanted to show that it's possible to also detect these things. So what are some potential mitigations for this? Well, one thing for the mobile attack is to, in the corporate setting, always keep VPN up. Sure, it's going to take more battery to maintain the network connection all the time, but at least you're going to be able to leverage your intrusion protection systems, your network-based host intrusion stuff, and be able to see some of these kinds of attacks as they're happening on the mobile device. So if you're not basically keeping the VPN up, you're kind of letting all that information go to the infrastructure, to the cell towers, and you're not being able to capture that sort of thing. So obviously that's a challenge, but if you can do it, keep VPN up and use your corporate infrastructure. Limit third-party applications and proactively analyze them. So, tear them apart, reverse engineer them, look at how they work. Also consider the ecosystem of how Android devices and other mobile devices interact with the broader scope of machinery out there. There is a bunch of data loss prevention software that can be deployed on the host. And one of the problems is that that's not properly configured. And it's also an uphill battle because it comes down to a black-white list on the DLP. So you might be able to detect that random devices are being plugged into, random USB devices are being plugged in, but how do you decide which ones you're going to allow and deny? So there's still that problem. And of course, use training and awareness. So that's basically it. I'm happy to take some questions. No, just the internet. Yeah. So the particular vulnerability that was exploited, the Exynos thing, just required the ability to read and write from the file system. So something like SE Android, which is a project that's starting to be used on some actual commercial devices, would have potentially protected something like that. Because SE Android is designed to prevent user space applications from basically doing anything they want. It's sort of a whitelist. I'm going to allow an application to only touch certain files on the file system, or I'm going to make off limits the whole /dev tree, the whole /proc tree, or whole directory of files. Pardon? C groups. I'm not familiar with C groups. Is that like user space, user mode Linux kind of thing where it's CH rooting? I'm not familiar. So is it SC Linux? Okay. Yeah, so it definitely would help to deploy those kind of things on these devices. It becomes a question of, are there still kernel vulnerabilities that I can attack? So, you know, if I'm still plugging in devices into my mobile device, you heard Travis and Sergey talk about all those drivers that exist in the kernel. So you still have to worry about that same attack surface because it sits inside the kernel. Any other questions?
Thank you very much.
Okay.